Hello and welcome to Earth Science, Lecture 25, The Ancient Roots of Astronomy. The science of astronomy provides a rational way of knowing and understanding the origins of Earth, the solar system, and the universe as a whole. Earth was once thought to be unique, different in every way from everything else in the universe. However, through the science of astronomy, we have discovered that our planet is similar to other objects in the universe, and that the physical laws that apply here on Earth also apply everywhere else in the universe. In this first lecture of astronomy, we will examine the transformation from the ancient views of the universe, which focused on the positions and movements of celestial bodies, mainly planets, to the modern perspective, which focuses on understanding how these celestial objects came to be and why they move in the way that they do. So first, before we get deep into the lecture, I just wanted to share one random image. So this here is just a picture of stars. Every dot that you see in this image is a star. To give you an idea, there's about 240,000 stars in this picture alone. And note that there is a line here. I didn't copy and paste this same image above. This is just an artifact from the imaging. So there's about 240,000 stars in this image. So this seems immense. This must be taken over a large area in space, right? Well, not so much. That image was taken from the pinpoint location right there at the tip of the arrow in the band of our Milky Way galaxy. So we had our telescope zoom in on that one pinhead point of a spot, and this is what we found, 240,000 plus stars. So let's begin by saying, what is astronomy? Well, the term astronomy is derived from the Greek root word of astron, which stands for star, and nomos, which stands for arrangement or law. So astronomy translates to the arrangement of the stars. Astronomy can also be said as the study of the origin and evolution of the universe, the physics and chemistry of celestial objects, and the calculation of their positions and motions. But to me, astronomy is more importantly described as being about us. As we study astronomy, we study ourselves and our place within the universe. So we seek to answer the biggest questions that exist. What are we? Where did we come from? Are we alone? And so on. Now, astronomy has many branches. So we'll just go through a list of some of the common branches of astronomy. We'll start with astrometry, which is the precise measurements of the positions of stars and planets. We have planetary science, which is the study of asteroids, comets, and the planets, so basically everything that makes up our solar system. We have stellar astronomy, which is the study of the origin, evolution, and deaths of stars, not just our sun. We expand a little bit further. We have galactic astronomy. This is the study of the structure and components or constituents of galaxies. Well, astrophysics is the study of the universe and the physics of its constituents, so things like luminosity, temperature, composition, and so on. Cosmology is basically the study of the universe as a whole, so this is the origin and evolution of the universe as a whole without just looking at single parts. And then a relatively more new field is astrobiology. This is the study of the possible life elsewhere in the universe. And just to be clear, astrology is not a science. Remember, there's a distinction between astrology and astronomy. Astrology is not a sound science. So let's jump into this lecture. So we mentioned that we're going to be looking at the history of astronomy a bit. So let's go very far back into ancient times. Careful observations of the sky have been going on for many thousands of years. Astronomy has been called the oldest of the sciences because its roots stretch deepest into antiquity. Ancient civilizations did not always practice astronomy in the ways for the same reasons that we study them today, but they nevertheless hold some amazing achievements. Understanding this ancient astronomy can give us a greater appreciation of how and why science developed through time. Interest in astronomy likely stemmed in part due to our fundamental curiosity, but ancient cultures had also discovered that astronomy has practical benefits for timekeeping, keeping track of seasonal changes, and navigation. Long before recorded history, people were aware of the close relationships between events on Earth and the positions of heavenly bodies. They realized that changes in the seasons and floods of great rivers, such as the Nile in Egypt, occurred when certain celestial bodies, including the sun, moon, planets, and stars, appeared in particular places in the heavens. Early agrarian cultures, whose survival depended on seasonal change, believed that if these heavenly bodies could control the seasons, they could also strongly influence all earthly events. These beliefs undoubtedly encouraged early civilizations to begin keeping record of the positions of celestial objects. One amazing example comes from the people of Central Africa. Although we do not know exactly when they developed the skill, people in some regions learned to predict rainfall patterns by making careful observations of the moon. So here you can actually see a chart describing how this works. So the orientation of the horns of a waxing crescent moon relative to the horizon. So when we say horns, we mean like the two ends of the moon. So its orientation or angle relative to the horizon varies over the course of the year. And this is primarily because of the angle at which the sun's path through the sky changes during the year. In the tropical regions in which there are distinct rainy days and dry seasons, rather than the 4 common seasons that we see here in the United States, the orientation of this moon can be used to predict how much rainfall should be expected over coming days and weeks. So you can see when the moon isn't really tilted at all, it's peak rainy season on average, and when it's tilted between, let's say, 25 degrees, we see that it's more of a dry season. So by looking at just the tilt of the moon, they were able to figure out basically if it was going to be more likely to rain or not on a given timescale. The impact of astronomical observations is still with us in our modern measure of time. The length of our day is the time it takes the sun to make one full circuit of the sky. The length of a month comes from the moon's cycle of phases. So think of the word month and how it relates to moon. So think moonth. The year is based on the cycle of the seasons, and the 7 days of the week were actually named after the 7 planets of ancient times, which were the sun, the moon, and the 5 planets that are easily visible to the naked eye, that being Mercury, Venus, Mars, Jupiter, and Saturn. So note planet in ancient definitions comes from the Greek word meaning wanderer. So this is applied to any object that appeared to wander in the fixed stars. So that is why the sun and the moon were actually on the list and Earth was not, because we don't see the Earth itself moving through the sky. So several of the English names came from Germanic gods. So for example, Sunday came from sun, Monday from moon. Tuesday, though, came from the Germanic god Tu, Wednesday from Woden, Thursday from Thor, and Friday from Freya, for example. The path that led to modern science emerged from the ancient civilizations of the Mediterranean and the Middle East, especially from ancient Greece. Greece gradually rose as a power in the Middle East beginning around 800 BC and was well established by about 500 BC. Although the early Greeks have been criticized for using purely philosophical arguments to explain natural phenomena, they employed observational data as well. The Greeks developed geometry and trigonometry and used the basics of these disciplines to measure the sizes of and distances to the largest appearing bodies in the heavens, that being the sun and the moon. In short, Greek philosophers developed at least 3 major innovations that helped pave the way for modern science. Oops, went the wrong way. First, they developed a tradition of trying to understand nature without relying on supernatural explanations, and of working communally to debate and challenge each other's ideas. Second, the Greeks used mathematics to give precision to their ideas, which allowed them to explore the implications of new ideas in much greater depth than would have been possible otherwise. And third, while much of the philosophical activity consisted of subtle debates grounded only in thought and was not scientific in the modern sense, the Greeks also saw the power of reasoning from observation. They understood that an explanation could not be right if it disagreed with observed facts. When watching the sun, moon, and stars rise along the eastern horizon and move across the sky, it seems reasonable to think that the Earth is stationary and that everything in the sky is moving around you. If you observe the skies as ancient astronomers did, you will also find that the stars seem fixed in their position relative to one another. Whereas 7 heavenly bodies, that again being the sun, moon, and the 5 visible planets, Mercury, Venus, Mars, Jupiter, and Saturn, they all seem to shift from night to night against the other stars. The Greeks imagined that the universe consisted of 8 transparent concentric spheres that revolved around a central, motionless Earth. The stars were fixed to the outermost sphere, and the 7 moving bodies each occupied one of the inner spheres. This conceptual model in which the heavens circled around a motionless Earth is called the geocentric view of the universe, or the geocentric model. Note that geo means Earth, and centric means centered, so it's quite literally the Earth-centered model. So here I have an image that just compares the Earth-centered model, or the geocentric model, to a merry-go-round. So our planets might be rotating in some direction, so we see child 1 and child 2 orbiting the center, and they seem fixed, right? The kids, if they're on, say, one of these fixed merry-go-round rides, they are not able to move in their own place. So we have our stars fixed on the outside with those merry-go-round seats, and then the children inside, maybe they're running around, even though that's usually not allowed, like the planets. They're wandering around the inside, but orbiting the center, the Earth. So this geocentric model quite literally put the Earth at the center of the universe. This idea was largely accepted because people can't sense Earth's motion, and Earth seems too large to spin. So, if you stand outside right now, it doesn't feel like you're spinning through space, so it's reasonable to think that the Earth was the center in ancient times. However, modern science, of course, has taught us that the Earth does indeed move, causing visible distant objects to appear to move across the sky. Earth's rotation was not confirmed experimentally, though, until 1851. Greek modeling of the cosmos culminated in the work of Claudius Ptolemy. In addition to presenting a summary of Greek astronomical knowledge, Ptolemy is credited with developing a detailed geocentric model of the universe known as the Ptolemaic system. Ptolemy's great accomplishment was the ability to adapt and synthesize earlier ideas into a single system that agreed quite well with the astronomical observations available at that time. In the end, he created and published a model that could correctly forecast future planetary positions to within a few degrees of arc, which is about the angular size of your hand held at arm's length against the sky. This was sufficiently accurate to keep the model in use for the next 1,500 years. The Greeks believed that heavenly things must be made of perfect circles, which they regarded as the purest geometric shape. And indeed, the sun, the moon, and the stars can be modeled as following circular paths around the Earth. But the motion of the 5 visible planets against the background stars is far more complex. Periodically, each planet appears to stop, reverse in direction for a week or months at a time, and then resume its forward motion through the sky. These apparent reversals in their motion are called retrograde motion, where retro means to go back, and gradus means walking, so it literally means walking backwards. To account for these motions, Ptolemy devised a complex system whereby planets move along small circles known as epicycles, while orbiting Earth on a larger circle called a deferent. His model predicted the motions of the planets with remarkable accuracy for at least a century. When it fell too far out of step with the observations, it was simply recalibrated using his new observed positions as a starting point. Ptolemy's model is, of course, not correct. This figure here shows the actual cause of retrograde motion for the planet Mars as an example. Earth takes less time to orbit the Sun than Mars, and because of that, it overtakes its neighbor. While Earth is, quote, passing Mars, as you see right on number 4 in the middle of this figure. So we're both moving around, but Earth moves faster since it's closer to the sun. At point 4, Earth is now overtaking Mars. So as a result, while passing Mars, Mars appears to be moving backward in retrograde motion. So you can see the path outlined here. So if you connect your sight to Mars, it looks at point 1 in the background, and then at point 2, then point 3. And then for a while, as we're overtaking Mars, it looks like it's moving backward. And then it continues that forward motion. Much accumulated knowledge disappeared as libraries were destroyed after the decline of Greek and Roman civilizations. And the center of astronomical study moved east to Baghdad, where fortunately, Ptolemy's work was translated into Arabic. When it was later reintroduced into Europe, it became fused with the teachings of the Church, which was a problem for those who would later question it. So, to give you kind of a good analogy for this retrograde motion, it's kind of hard to visualize a planet moving backward, even with this graphic here. So what I recommend is think about driving down the highway. So you're driving in a, let's say, 2-lane highway, and let's just say you're in the fast lane and you have a car ahead of you in the slow lane on the right. Well, as you go past that car, even though you're both moving forward down the highway, to you, because you're moving faster, as you overtake that car, from your perspective, it looks like that car is moving backward. And so that's a good analogy here. The only difference really is the speed at which the planets are orbiting. So there's not a ton that we're going to go into detail with in ancient astronomy for this lecture, at least. But I just wanted to throw this timeline in here so you at least get an idea of when certain ideas came about. And I'm just going to highlight a few. So let's look at Aristarchus, which is from 310 to 230 BC. The first Greek to profess a sun-centered universe was Aristarchus. He also used simple geometric relations to calculate the relative distances from Earth to the Sun and the Moon. He later used these data to calculate their sizes. As a result of an observational error beyond his control, he came up with measurements that were much too small. However, he did discover that the Sun was many times more distant than the Moon, and many times larger than the Earth. The latter fact may have prompted him to suggest a sun-centered universe. Nevertheless, partially because of the strong influence of Aristotle's writings, the Earth-centered view dominated Western culture throughout the next 2,000 years. And we'll look at Aerith Anis as well, the last person on here. Contrary to common belief, the explorer Columbus did not prove that the world is spherical rather than flat. The Greeks had assembled convincing evidence that Earth is a sphere. For example, the famous Greek philosopher Aristotle pointed out that Earth must be spherical because it always casts a curved shadow when it eclipses the moon. The first successful attempt to establish the size of the Earth is credited to Aerith. I can't say his name. Aerith Anis. You get the idea. I'm sorry, I forgot to listen to the name before starting. Anyway, he observed the angles of the noonday sun in 2 Egyptian cities that were roughly north and south of each other, that being Syene and Alexandria. Finding that the angles of the noonday sun differed by 7 degrees, or 1/50th of a complete circle, he concluded that the circumference of the Earth must be 50 times the distance between those 2 cities. The 2 cities were 5,000 stadia apart, so Eratosthenes came up with a measurement of 250,000 stadia. Many historians believe that a stadia was 517 feet, which would make his calculations of Earth's circumference, which was 24,428 miles, very close to the actual value of 24,902 miles. So at this point, please pause the video and watch the Earth's circumference video found in the YouTube description, or at this link. And then here's the other end of that timeline for major Greek figures. So we're going to go into some of these a little bit more later on, but hopefully this timeline at least could be a good reference for you as you study a little bit. Okay. Modern astronomy developed with a bit more of a scientific endeavor, so it required a break from the deeply entrenched Western philosophical and religious views that had been held for thousands of years. This transition was brought about by the discovery of a new and much larger universe governed by discernible laws. We examine the work of 5 noted scientists involved in this progression from an astronomy that merely described what is observed to one that tries to explain why the universe behaves as it does. And so Nicholas Copernicus, Tycho Brahe, Johannes Kepler, Galileo Galilei, and Sir Isaac Newton are those figures we will focus on. The Greeks and other ancient peoples developed many important scientific ideas, but what we now think of as science arose during the European Renaissance. Within half a century after the fall of Constantinople in 1453, Polish scientist Nicholas Copernicus began the work that ultimately overturned the Earth-centered Ptolemaic or geocentric model. Nicholas Copernicus was born in Poland on February 19th of 1473. His family was wealthy, and he received an education in mathematics, medicine, and law. He began studying astronomy in his late teens. By that time, tables of planetary motion based on the Ptolemaic model had become noticeably inaccurate. But few people were willing to undertake the difficult calculations required to revise such tables. For almost 13 centuries after the time of Ptolemy, very few astronomical advances were made in Europe. After discovering Aristarchus' writing, Copernicus became convinced that the Earth is a planet just like the other 5 known planets at the time, and that the planets orbit the Sun, after recognizing that much simpler explanation for apparent retrograde motion offered by a sun-centered system. This heliocentric or sun-centered model was a major break from the ancient and prevailing idea that a motionless Earth lies at the center of all movement in the universe. He went far beyond Aristarchus in working out mathematical details of the model. Through this process, Copernicus discovered simple geometric relationships that allowed him to calculate each planet's orbital period around the Sun and its relative distance from the Sun in terms of the Earth to Sun distance. Despite his own confidence in this model, Copernicus was hesitant to publish his work, fearing that his suggestion that Earth moved would be considered absurd. However, he discussed his system with other scholars, including high-ranking officials, who urged him to publish a book. Copernicus saw the first printed copy of his book concerning the revolutions of heavenly spheres on the day that he died, May 24th, 1543. Publication of the book spread the sun-centered idea widely, and many scholars were drawn to its aesthetic advantages. Nevertheless, the Copernican model gained relatively few converts over the next 50 years, and for a good reason. Unfortunately, it didn't work quite that well. Copernicus retained a link to the past, and used circles to represent the orbits of planets like those of the ancients. Because of this, he was unable to accurately predict the future locations of planets and found it necessary to add smaller circles, those epicycles, like Ptolemy had to use. In the end, his complete model was no more accurate and no less complex than the Ptolemaic model, and few people were willing to throw out thousands of years of tradition for a new model that worked just as poorly as the old one. Part of the difficulty faced by astronomers who sought to improve either the Ptolemaic or Copernican system was a lack of quality data. Better data were provided by the Danish nobleman Tycho Brahe. Tycho Brahe, who lived from 1546 to 1601, is a Danish nobleman and was born 3 years after the death of Copernicus. Tycho reportedly became interested in astronomy while viewing a solar eclipse that astronomers had predicted. His family discouraged this interest. He therefore kept his passion secret, learning the constellations from a miniature model of a celestial sphere that he kept hidden. As he grew older, Tycho often became arrogant about both his noble birth and his intellectual abilities. At age 20, it is noted that he fought a duel with another student over which of them was the better mathematician. part of Tycho's nose was cut off, and he designed a replacement piece made out of silver and gold. And I must mention that he has a fabulous mustache as well. In 1563, Tycho decided to observe a widely anticipated alignment of Jupiter and Saturn. To his surprise, the alignment occurred nearly 2 days later than the date that Copernicus had predicted. Resolving to improve the state of astronomical prediction, he set about compiling careful observations of stellar and planetary positions in the sky. Tycho did not believe in the Copernican model because he was unable to observe the apparent shift in the position of stars that should result if the Earth did travel around the Sun. He argued that if Earth orbited the Sun, the position of any nearby star, when observed six months apart and hence from opposite sides of the Earth, like you see in this picture, they should shift with respect to the more distant stars, a phenomenon called stellar parallax. So stellar parallax is just the effect of you looking at the same star from two different perspectives, and as a result, it appears like it's in two different spots in the sky. So perhaps at one point in Earth's orbit, you're looking at it from here, and so it appears to the left, but then you look at that same object a little bit later on, and now it's appearing against those stars in the background on the right. So that's called stellar parallax. Parallax is actually easy to experience. In fact, you should do this. Hold out your finger in front of your face, and close one eye, and then the other. And observe how your finger seems to shift its position against background objects. Now hold your finger further away, and notice that the apparent shift is smaller. Therein lies the flaw in Tycho's argument. He was absolutely right about parallax, but the distance to even the nearest star is so significant compared to the width of Earth's orbit that he was unable to observe any parallax. Today, space-based telescopes use parallax to measure distances to stars in our galaxy. But Tycho's fame grew after he observed what he called a nova, meaning new star, in 1572. By measuring its parallax and comparing it to the parallax of the moon, he was able to prove that the nova was significantly further away than the moon. Today, we know that Tycho saw a supernova, the explosion of a distant star. King Frederick II of Denmark decided to sponsor Tycho's ongoing work, providing him with money to build an unparalleled observatory for naked eye observations. There, he designed and built pointers. The telescope would not be invented for a few more decades, so no telescope yet. But these pointers were used for 20 years to systematically measure the locations of the heavenly bodies in an effort to disprove the Copernican theory, or the sun-centered model. Over a period of 3 decades, Tycho and his assistants compiled naked-eye observations accurate to within less than 1 arc minute, that is, less than the thickness of a fingernail viewed at arm's length. Because the telescope was invented shortly after his death, Tycho's data remains the best set of naked-eye observations ever made. Despite the quality of his observations, Tycho never succeeded in coming up with an explanation for planetary motion. And so that will segue us into our second lecture on this topic. So let's close out the lecture with 3 questions. Number 1, who is credited with developing a detailed geocentric model of the universe? Okay, in this case, geocentric is that, there's another name for that. It's literally called the Ptolemaic model, so the guy is Ptolemy. The Ptolemaic system is the one that places the Earth at the center. It's also called a geocentric model. Number 2, who was the first to propose a heliocentric model for the solar system? So out of these people, it is Nicholas Copernicus. This model was a major break from the ancient times and the prevailing ideas that a motionless Earth lies at the center of all movement in the universe. And last but not least, the first recorded effort to measure the circumference of the Earth was made by Aerith Anis, and he used what to do this? All right, and in this case, it was the difference in the angle of shadows at 2 different locations, a known distance apart on the same day. He observed the angles of the noonday sun in 2 Egyptian cities that were roughly north and south of each other. Okay, so that's it for this lecture. So the very first astronomy lecture. We're going to finish up our history of astronomy by continuing our discussion from where we left off. So what we're going to do is look at some of the mathematicians that came in and helped describe everything we were seeing. So we have observations, thanks to Tycho, but we don't really have an explanation as to why things moved. So we'll learn about that next. As always, thanks for watching and have a great day.